MDM4U, a formula that is given to us in the textbook is Sn is equal to n times n+1 over 2, which is the sum of the first n natural numbers. So that means if we add up numbers like 1, 1 plus 2, 1 plus 2 plus 3, these consecutive numbers, when we add them together, what is their total? So we can do this by hand, but eventually we want to know what is this in general. So we're going to start off with an algebraic proof for the sum of the first n natural numbers. Let's break this into two different cases. Let's first inspect what's happening when we have even numbers. So even is anything divisible by 2, so this is the sum of the first 2, 4, 6, 8, 10, and in general, the sum of the first n numbers. So we have here 1 plus 2 is 3, and here we have 1 plus 2 plus 3 plus 4 is equal to 10. Look at this addition sign in the middle. I've highlighted it because if we look at the left and right hand side and pair these values, 1 and 2 is 3. Here we pair 1 and 4, so the outermost values, 1 and 4 is 5. But 2 and 3 is also 5. Similarly, 1 and the last, so the first and the last paired together is 7 in this case. 2 and 5 is 7, and 3 and 4 is also 7. So that's 3 times 7. And we're starting to see this pattern when pairing the outermost values. 1 plus 8 is 9. 2 plus 7 is 9. Another group of 9 and another pairing of 9. I feel like that is an error. Let's fix that. Similarly, 1 and 10 is 11. 2 and 9 is 11, and so on. We're getting pairings of the same value when we group them together. So, if we look at this in general, how is 5 related to 10? How is 8 related to 4? How is 6 related to 3? 4 related to 2, and so on? Well, that's always half of that value, n. So we can say this is n over 2. And similarly, this right here, how is 11 related to 10? How is 9 related to 8? How is 7 related to 6? That's always plus 1. So we can call this n plus 1. And just by multiplying n times the numerator here and pretending this is division by 1, 2 times 1 is 2, this looks like that formula in general. That's just for the even cases. So let's see how this looks for odd cases. So we have 1 plus 2 plus 3 because we have 1, 3, 5, 7, 9. These are our odd numbers. And we try to see what is happening. If we do this here, we end up with grouping these together. We have, well, just 1, but 1 and 3 grouped together is 4. And then 1 plus 5 is 6, and then there's another 6, but we have the 3 in the middle. So we're still getting that pairing of outermost values, 1 and 7, then 2 and 6, 3 and 5, all of those adding up to 8. So we have 3 groups of 8, but then we also have a 4 in the middle. So let's see, when we do that same technique, grouping the outermost values, what happens to our sum? Well, how are these numbers related to the general term n? 9, how is that related to 10? How is 7 related to 8? How is 5 related to 6? And how is 3 related to 4? In each of these cases, we have n plus 1 for this factor here. So that's where we get n plus 1 for the general statement. But that first number, we have 0, 1, 2, 3, 4. That's a pattern. But how is 1 related to 0? How is 3 related to 1? How is 5 related to 2? In each case, this is 7 and 3, 9, and 4. This one's a little bit less obvious, but if we take 1 away from this value and then divide by 2, we end up with that number. And then that number that's being added at the end, 1, 2, 3, 4, 5, how is that related? This is 1 to 1, 3, 2, 5, 3. If we add 1 to this number and divide by 2, we get this term that's being added at the end. So what we need to do from this point here is algebraic manipulation, just meaning we can multiply both sides by 2 to get rid of, we have a division by 2 here and division by 2 here. We would then end up with 2 times the sum up to n is equal to this algebraic expression. Just getting rid of those 2's in each term by multiplying each side by 2. Then we can use we can multiply these two binomials using FOIL, and we end up with the following expression. Notice that that's a difference of squares. And when we minus 1 plus 1, those terms will cancel. We'll have just n squared plus n, and we can take out the common factor. And then if we want to isolate our variable Sn, we just divide each side by 2, and we have the same formula, even though it was approached differently. So whether even or odd, we end up with that same general expression for the sum of natural numbers up to n. Next. Geometric proof. So same thing that we're trying to prove, but let's take a look at this technique, and I think this is very clever. If you double each sum, then the triangle pattern will form a rectangle with side length n and width n plus 1. So here's 1, and what we're doing is look at this left column first. All we're doing is showing that this is forming a triangle pattern, and we're adding consecutive numbers. Okay? Now if we double this pattern and put them side by side, this will form a rectangle where this is technically length 1 and 2, so that's n and n plus 1. And this right here is, if we rotate and attach it back to itself, it'll form a rectangle where this is length 2, but this is length 2, but this is length 2 plus 1. And in every single case, we're going to end up with that same situation. We have, this is S3, so its length will be 3, but its width will always be plus 1, because it'll fit as a rectangle in this shape, no matter what n is equal to. So what does that say about a general statement? Well, this is like, using our length times width formula, the length times the width for this rectangle. But this rectangle is double the sum up to n. Notice that here it's just 1, so when we double it, that's 2s1. And then we get the length times width formula to be the following. Now, think of how is n related to this right here. This is always, in each of those cases, let's just use this. 5, how is it related to 5? How is it related to 6? How is 4 related to 4? How is 4 related to 5? This is always n and n plus 1. And this is 2 times that sum of natural numbers up to n. So if we isolate our variable, Sn, we divide each side by 2, we end up with the same formula. So just 2 interesting proofs for the sum of the natural numbers up to n.